In this video, we are going to go through 7.2 and talk about the ambiguous case of the law of sines. When we introduced the law of sines in 7.1, we addressed the fact that there are 4 different cases for information around oblique triangles, and 3 of them are kind of set in stone. You know, if you have this set of information, this is what you're going to do. But that 4th one, well, actually it's case 2, but the 4th of the 3 cases that we didn't discuss is ambiguous. Let's talk through some of these. One of our cases for congruencies, for congruent oblique triangles, is not angle, angle, angle. You remember when we discussed angle, 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 this gives us similarity, not congruency. There's my symbol for congruency, the little curve above the equal sign. Similar triangles are the same shape, but they're different sizes. If I know that my angles all have the same measure and that I can have corresponding angles, so for example, this is ABC, this is A prime, B prime, C prime, they have the same measure, but the distance between A and C is not preserved from my first triangle to my second triangle. This triangle is the same shape, but it is larger. So that's a case for similarity, not congruence. Let's review our 3 congruency cases that we worked with from 7.1, and then we will address the ambiguous case. All right, case 1 is when I know 2 angles and any side. So it can be angle, angle, side in order, or angle, side, angle. That doesn't matter. It has to be the same. We know that these triangles are going to be congruent if we have these 3 corresponding pairs. Because, for example, if I know each triangle has a 40-degree angle, a 60-degree angle, and a side that is 5 centimeters, well, I automatically know, let's sketch a triangle, and I don't know that this triangle is going to be accurate at all. But so we've got a 40 and a 60. Let's say this is our 40-degree angle, and this is our 60-degree angle. Well, what does angle B have to be? Well, angle B must be 80 degrees. It just has to be. So that 5 centimeter side is a set distance, whether it's here or over there. We're going to be able to solve using our law of sines. The next case that we discussed was labeled case 3. We're going to talk about case 2, that ambiguous case at the end. Case 3 is when I know side, angle, side. I know 2 sides and the angle included. That order absolutely matters. For example, I might know that angle A is 50 degrees, side B is 3 centimeters, and side C is 5 centimeters. Well, if I know that, then let's do this. This is a 50-degree angle A. So side A is going to be over here. Side B is going to be 3 centimeters, so that means this is angle B, and side C is 5 centimeters, so this has to be angle C. Because of the way the triangle is structured, because I know how far apart these rays are, they open at 50 degrees, and I know I'm going to draw this segment 5 centimeters and stop. And then I know I'm going to draw this segment 3 centimeters and stop. There's only one way to connect B to C. This side has to be this length because of the structure that I started with. All right, case 4. If I know 3 sides, then I know the shape of my triangle. For example, if I know I have side lengths 6 centimeters, 5 centimeters, and 4 centimeters, they're only going to fit together one way. They're only going to fit together one way. It doesn't matter how I rotate, orient my triangle. I've got a 6, a 5, and a 4. I can turn that. It's still going to be the same shape, though, even if I turn it. I can't turn it. I know me. I can't turn it and make it look the same. But if this is my 4, my 5, and my 6, I can rotate that around and I can lay one on top of the other and they are going to match up. It's only one triangle because there's only one way I can stick those sides together and have them come out to look like a triangle. But but case 2 is my ambiguous case. I know side, side, angle, or angle, side, side, because it is a pain in the, where that angle is not included between the two sides. Now, when that angle is not included between the two sides, I don't have a guarantee in what my triangle is going to look like. Now, we have a nifty hands-on activity that we would do if we were in class. We're not in class, so I'm going to try just to explain it to you with the drawing. So side, side, angle. Side, side, angle means that I've got the start of a triangle. Let's say I know that this is a 60-degree angle, and I know that this side is 7 centimeters, and I know that this side is a certain length. So I know this side. So I may know angle A, side B, and side A. I don't know side C. Now, depending on how long this side is, I have some options. If it's too short, I have 0 triangles. Because if it swings down and it doesn't meet, if it's not tall enough, then it's not going to work. If it's just exactly the shortest distance, I would have 1 triangle. I would have a right triangle. Or say it's really long. I swing it way out here. I've got 1 triangle, because if I took this side, think of it on a pivot, that I can pivot this side around. If I swing it over here, it works. I can extend this base to match. But if I swing it back over here, it would swing in an arc that would not meet over there. And so I would just have 1 triangle. So I have a possibility of 1 triangle if it's really long, or if it just barely meets and makes that right triangle. I've got 1 triangle. But what if this side A is long enough that when I swing it down here, it would intersect here and form a triangle, or if I swing it this way on that arc, it would intersect here, and the same side length would form 2 different triangles. It would form this triangle, A, B, C, or it would form this triangle, A, B, C. Either an acute triangle or an obtuse triangle, depending on where this side lengths intersected the line. So I might have 2 triangles. If I have kind of just the right, I have this range of side lengths that fit so that when I connect it here, it could either intercept this other side here or there. If I have this side-side angle or angle side-side case, I can't be sure whether I have 0, 1, or 2 triangles. Okay, applying the law of sines. These are 3 things you need to remember. Remember these 3 things. Absolutely remember these 3 things. For any angle theta of a triangle, the sine of theta is going to be between 0 and less than or equal to 1. So between 0 and 1. If sine of theta is 1, then theta is 90 degrees and I have a right triangle. If sine of theta, I know that the sine of theta is equal to the sine of the supplementary angle. Supplementary angles have the same sine value. Now let's look at that. If I have, well, let's just do this. I have a sine value of 1/2 here. I have a sine value of 1/2 here. What angle has that sine function value of 1/2? Well, that's my 30-degree angle. So for 30 degrees, I have the same sine function value, a positive 1/2. What about this one? Well, this is going to be 30 degrees away from that x-axis. That's a 150-degree angle. Has the same sine function value. If I add these angles together, they add to 180 degrees. So I have 2 different angles who have the same sine function value. And then our third thing that you need to remember is that the smallest angle is opposite the shortest side, the largest angle opposite the longest side, and the middle value angle opposite that intermediate side length. That is always going to hold true for any triangle. Okay, let's practice some using this ambiguous case law of sines. Remember that your starting place should always be sketching a triangle. You have to make sure you have the right piece of information in the right spot. So let's sketch our triangle. We know angle C, so this is going to be angle C right there. 75 degrees, 30 minutes is angle C. Side C is going to be opposite angle C. Side C is 13.2 centimeters. Notice I didn't connect that yet. This is the ambiguous case. I don't know for sure whether or not I have a triangle yet. So let's label this ABC. I know side A is 17.9 centimeters. I know side C is 13.2 centimeters, and I know angle C is 75.5 degrees. So that's my setup. Now I have a choice with how I can approach this. I could see what the height of this is, because I know that this is angle C, this is opposite, this is hypotenuse. And I know that sine is opposite over hypotenuse. So if I take sine of 75.5 degrees and I set that up as sine of 75.5 degrees is equal to that opposite, which would be the height here, over the hypotenuse, 17.9. So I multiply both sides by 17.9 and I can solve for h. Well, h, the height, if I do a perpendicular line drop down from vertex B to this side B, I discover when I plug that into my calculator that my height is going to be about 17.3 centimeters. Well, this is only 13.2, which means this side is too short to form a triangle. That's one way to say, you know what, we are not going to have a triangle. No triangle exists here. Another way to see whether or not you have a triangle would be to use our law of sines. Now, we know this angle and the opposite side. We know this side, so we could set up the law of sines using angle A. Since we're solving for the angle, we're going to put that on top. Sine A over 17.9 would be equal to the sine of 75.5 degrees over 13.2. To solve for that, I'm going to multiply cross products. So I get sine A times 13.2, which means then I'm going to need to divide by that 13.2 to solve. So I get sine A is equal to 17.9 times the sine of 75.5 degrees divided by 13.2. When I plug that into my calculator, and make sure it matters, it absolutely does matter, make sure that you are in degree mode. So I'm going to plug this into my calculator, make sure I'm in degree mode, clear. I've got 17.9 times the sine of 75.5 degrees, and then I take that and I divide that by 13.2. I get 1.31, etc. that as my sine function value. Now, when you get to this point, you may say, oh, sine function cannot be greater than 1, it can't be out beyond that 1, -1, or you may not. And if you don't recognize that and say, oh yeah, that's not going to work, then you do sine inverse of this value. So I could do inverse sine of that answer, so I don't even have to round it. I get a domain error. That domain error says, oh wait, that cannot be a sine function value for any angle ever. So that tells me that that does not exist when I use sine inverse, so there is no such triangle. All right, I've warned you that I have always added more examples than I need to. This is going to be another no such triangle. I want you to sketch this triangle, make sure you get your sketch correct, and make sure you get that solution that it does not exist, that you have no triangle here. Your sketch should end up, based on what you know angle B, so this is going to be B at 55 degrees 40 minutes, which 40 minutes is 40 over 60 minutes out of 1 degree. When I plug that into my calculator, I do 55 plus 40 over 60, and then I close my parentheses. Side B is opposite angle B, so that's 8.94 meters. Side A, I'll put that up here at 25.1 meters. And I can use my law of sines, or I can solve for the height of that triangle. All right, let's look at the next page. Okay, so what if this is the set of information we're given? We're given angle A, side B. So I start my sketch. I've got angle A, and side B. Angle A is 61.4 degrees. Side A is 35.5 centimeters. Side B is 39.2 centimeters. And I'm supposed to solve the triangle. So I'm going to start by using law of sine to find this angle B to see if it's going to work. So my first step is to say sine B over 39.2 centimeters equals sine of 61.4 degrees over 35.5 centimeters. Remember, I'm going to use my cross products. When I use my cross products, I find that the sine of B should come out to be about, and I'm not going to round it off in my calculator. I'm going to use it in my calculator just like I did before. Let me show you that one more time. I'm going to plug this in and I'm going to say, all right, I'm going to say 39.2, let me get that glare off the screen, 39.2 times the sine of 61.4 degrees. I'm in degree mode. And then I'm going to need to divide that by 35.5. And there's what I got that I rounded off when I wrote it down. But I'm not going to round it. I'm just going to use it. And I use it by saying sine inverse of that value. Sine inverse of that value is going to give me the approximate measure of angle B. Capital letter for an angle. So sine inverse of that answer gives me angle B as about 75.8 degrees. So angle B is about 75.8 degrees. I have solved and I've found that this works. So if I have one triangle, I'm going to have to check to see if I have two. So when I find that that works, I immediately go, you know what? This is my first possible angle B. Since I've got an angle B, angle C is easy. To find angle C for this first triangle, and we're going to look to see if we have a second, to find angle C, we just do 180 minus the given angle minus the found angle. Gets us an angle value for C, an angle measure of C is about 42.8 degrees. So we have all three angles. Now we need our third side. The side we still don't know is side C. So the side C, little c1. I'm going to use my sine, law of sines to find that. I always use my givens as much as possible. So I'm going to start with this setup right here. And I'm going to set that equal to my sine of this angle value over my unknown length. Except I'm going to keep my unknown in the numerator. So I'm going to do c sub 1 length over sine of angle C is equal to that 35.5 over the sine of 61.4 degrees. Those are my givens. And when I plug that into my calculator and I simplify, I get that this side length for C, for this first triangle, is 27.5 centimeters. So that triangle is solved. Now, because this is my ambiguous case, if I have one triangle, I have to check to see if the other triangle exists. Now, I got a sine function value of 0.9695. Sine is positive in two quadrants, quadrant 1 and quadrant 2. Sine value is a positive value here at 75.8 degrees. It's also going to be positive here at whatever this angle is. Now this angle is 180 minus 75.8 degrees. So if I have a second angle B, it's going to be at 180 minus 75.8 degrees because that puts me at that location where I have the same sine function value. Again, think about your unit circle. Sine is positive in quadrants 1 and 2. If it's a positive 0.9695, that sine function value here at 75.8 degrees, it also reflects across into quadrant 2. It is that same sine function value here at this angle. And I find this angle using that reference angle 75.8 degrees. So 180 minus that 75.8 gives me a potential second angle B for a second shape of this triangle. 180 minus 75.8 degrees is 104.2 degrees. If my second triangle exists, that would be the measure of that angle B. That would be if I took this side and it crossed here, that worked, and then if it crosses over here and that works, and I have this obtuse triangle. Let's see if it's going to work. We know it works if angle C exists for this triangle. So I take my given angle, I add my found angle, and if there is something left over for angle C, then this triangle exists. And there is, because 104.2 plus 161.4 comes out to be 165.6, which means that angle C is going to be 180 minus that 165.6. So my angle C for this triangle comes out to be 14.4 degrees. I do have a second triangle that exists. I have the acute triangle here, and I have that obtuse triangle with these angle measures. Well, if angle C is smaller in my second triangle than it was in my first triangle, that means side C is going to be shorter than it was in my first triangle. So I need to find side C, C sub 2, over the sine of this measure for angle C. I still use the same given statement. I'm still using this 35.5 over the sine of 42.8 degrees. I plug all that into my calculator. I multiply cross products. 35.5 times sine of 14.4 is divided by sine of 42.8 degrees is, and I get that the measure of side C is about 10.1 centimeters for this second triangle. So I have two triangles that exist here. Let's do another example of two triangles. I'm given angle A, side B again. So I'm just going to sketch my same triangle, angle A. In this case, angle A is 55.3 degrees. Side A is 22.8 feet. Side B is 24.9 feet. And I need to find my missing pieces to see if a triangle exists. And if a triangle exists, I've got to go back to see if a second triangle exists. So if there's a first triangle, there may be a second, and I will need to check for that. All right, let's walk through this and solve. If I'm going to use law of sines, I'm going to use the setup. I need to solve for angle B first. It's opposite the side that I know. So my first step is going to be to say, okay, if I have a triangle, it's going to be sine of B over 24.9 equal to sine of 55.3 degrees over 22.8. Since this side is shorter, I know that this angle B is going to be smaller than this angle. When I solve for that, I get a value of the measure of angle B, proposed first B, as about 63.9 degrees. Okay, acute triangle here. So I know that the sine function value I got is in quadrant 1. Then I need to find angle C. Angle C for this triangle is going to be 180 minus the given angle minus the found angle. So angle C comes out to be 60.8 degrees. I solve finally, so that's the second step, and then the third step is to solve for side C. Side C over sine of angle C equals to my given proportion, 22.8 over sine of 55.3 degrees. I come out with a length of side C as about 24.2 feet. So there I was given 3 pieces of information. I found the other 3, that triangle is solved. But wait, there's more. Well, there may be more. We have to stop and check, because I found an angle in quadrant 1, angle B, as 63.9 degrees. I'm going to have an angle in quadrant 2 that has the same sine function value as 63.9 degrees. It's going to be the supplementary angle to that. So let's see what that would be. If there's a second triangle, then it would be 180 minus 63.9 degrees. My second triangle would have an angle B with a measure of 116.1 degrees. If this second triangle exists, then when I take my given angle A plus this obtuse angle B, it will be less than 180 so that there is room for an angle C. And it is less than 180. This angle C comes out to be 8.6 degrees. So I have all three angles. Angle A is 55.3 degrees, that was given. I have an obtuse angle B, and then I have an angle C. This angle C is significantly smaller than the angle C in my first proposed triangle, where I had an acute triangle, acute angle, acute angle, acute angle. Now I have an obtuse triangle. This angle C is much smaller, which means the side opposite it is going to be much shorter. I need to find the length of that side using my givens as much as I can. And I find that the length of the side opposite angle C for the second triangle would come out to be about 4.14 feet, I have in my notes. Okay, let's look at that next page. Let's try another instance of this ambiguous case. We're going to solve the triangle. We're given angle B this time, side B and side A. I always orient my triangles the same way just because this is the way I feel comfortable doing it. You don't have to always orient them this way. So I've got this triangle. B, side B is 25.4 inches. I know angle B. I'm going to put angle A down here this time. I know that this side is 19.6 inches. So I'm going to start off solving. My first piece of information that I need, that I can find, is angle A using my law of sines. So that's where I start. So sine of A over the side length, sine of B, which I know, over its side length, and I solve for sine of A. I get the value of sine A is about, and remember I'm going to write this down for us, but you shouldn't need to estimate it here. You're not going to round it here. You're going to use the value in your calculator, taking sine inverse of that answer, and you get an angle A measure of 46.0 degrees. Now we're going to go ahead and keep that 0.0 because we're using 3 significant digits in our given information. So we're going to keep 3 significant digits here. So that's the approximate value for angle A in our first proposed triangle. We have a triangle that exists. If we have one triangle, we know we've got to stop and check to see if we have a second triangle. All right, let's finish solving our first triangle before we go look at our second. If you find this first triangle, if you know you have the ambiguous case, you find the first triangle, if you will automatically set up your page to remind you to check for that second triangle, it will be helpful. Okay. Second piece of information I find is going to be that missing angle C by taking 180 minus the given angle minus the found angle. And I know that angle C would be 65.3 degrees. And then the third thing I do is find that missing side. So side C over the sine of angle C is equal to this given ratio, 25.4 over sine of 68.7. Remember, the way I write my ratio depends on what my unknown is. I always try to put my unknown in the numerator. This gives me a length for side C as 24.8 inches in my first triangle. Angle C is 65 degrees. It's just a little bit smaller than angle B. So side C is a little bit shorter than side B. That makes sense. Angle A is our smallest angle, so side A is our shortest side. All right, let's check for that second triangle. So we have an angle here with a sine function value of 0.7189. That angle A, is 46.0 degrees, which means that I have another angle in quadrant 2 that has that same sine function value. And it is supplementary to 46 degrees. So if I have a second angle A, it will be 180 minus 46 degrees. So my second angle A, if the second triangle exists, is going to be 134 degrees. 134 degrees. Okay, does my second triangle exist? Well, I take my found angle A, second proposed angle A, I add it to my given angle, and 134 plus 68.7 degrees is already more, it comes out to be 202.7 degrees. That is more than the sum of the 3 degrees in my triangle. So that does not work. There is no second triangle in this case, because the other angle A that would have that same sine function value is too big. This angle A would have to swing out too far. It doesn't give you an opening that's going to give you a triangle. If I add it to my given angle, it's not going to work. Look at this next one. Try setting it up and see what you get. Don't forget to sketch a triangle first. I'm going to encourage you to pause the video, do it on your own, and then come back to look to see if our answers match. Let's come back and see how you did. We sketched our triangle, filled in the information we knew, discovered that what we can find first is this angle C. When I use my law of sines, I get a value of angle C as 27.6 degrees, which means that angle B would have to be 108.9 degrees for this triangle. I have a triangle that exists, so I automatically set up and say, okay, I got to check for that second. Then I come back over here and I find my last missing piece of information, the length of side B. I check to just kind of make sure that proportionally everything is correct. My shortest side is opposite my smallest angle. My longest side is opposite my largest angle. That all looks good. And then I come over here and I say, okay, if my found angle, and that's what I'm looking for, is my found angle. My first found angle, according to the information, was 27.6 degrees. If that exists, then there may be another triangle with the other angle whose sine is the same value. It would be in quadrant 2, and it would be supplementary because it would be 180 minus that 27.6. Well, 180 minus 27.6 is 152.4 degrees. If I have a second triangle, angle C in this second triangle would have to be 152.4 degrees. Does that work? Well, my given angle A is 42.5 degrees. So when I add that angle A to my angle C, that doesn't work because it's more than 180. So there is no second triangle. There's no second triangle. Okay. Let's look at our last example, our last set of practice problems. We've got a couple where we are analyzing data. Without using the law of sines, explain why no triangle ABC exists that satisfies this set of values without doing any math. So just look at your values and tell me why this can't happen. You may have to stop and do a sketch. What I see is that I've got the measure of angle B given to me as 93 degrees. What type of angle is that? Well, it's an obtuse angle because it's greater than 90. How many obtuse angles can a triangle ever have? Only one, because the other two angles have to share the remainder of the degrees out of 180, the sum of 180. So if this one is more than 90, then the other two have to split the remainder. They can't be obtuse, which means that since this is obtuse, it is automatically the largest angle. Well, the largest angle has to be opposite which side? Has to be opposite the longest side. If you look back at your information, side B opposite angle B is 42 centimeters. Side C is the longest side, which means the measure of angle C needs to be greater than the measure of angle B. So this triangle is not possible. Read through the next one. There's my reasoning. Because side B is longer than side A, that means the measure of angle B has to be greater than the measure of angle A. Measure of angle A is obtuse, therefore not a triangle.